So far we have done a very rigorous study of the direct stiffness approach in 2D structures as well as 3D structures, and we have derived some basic formulations. However, we have made some simplifying assumptions also, such as all the supports, they are fixed only. We have also made the assumption that all members are prismatic, and also that the floor slab, if it's present, does not offer any stiffness in the lateral direction. Its role is only for vertical load distribution. Now we release some of these assumptions one by one, and we go into the world of complications. So we begin with the consideration of the thermal effect. So let's say we have a structure, and here for simplicity we are considering this for 2D structures. However, the concept can be very easily extended to 3D structures also. Let us say in one of the members there is a rise of temperature delta T, and we assume that it's uniform throughout the member. So how do we tackle that? Now before we see this, let's consider the case of determinate versus indeterminate structures. How the two behave differently under thermal conditions. Let's say if there is a determinate structure and if there is a change in temperature throughout the structure, what will be the effect? The effect will be that it will undergo thermal strains, but it will not develop any stresses. This is true for a determinate truss also. On the other hand, if the structure is indeterminate, that is, it has restraints over and above the minimum necessary, then any temperature variation will give rise to stresses. So this is the difference between the determinate and indeterminate structures. That in the case of determinate structures, there will be free thermal strain but no stresses. Now we come back to this particular structure. So how do we handle the case of the temperature effect? We do as usual. Our objective is to incorporate all these additional effects such that we don't disturb the general framework of computations that we have so far developed. So first of all, we have to number the degrees of freedom, and we start with the unrestrained joints. We number the degrees of freedom there, and after having done that, we come to the supports where we identify and label the degrees of freedom associated with reactions. So here these are shown in black color. Now after this, what we do is that we have to consider the case of the temperature effect in some easy way. So let's study that. So in general, if the particular member which is undergoing temperature rise, if it was allowed to undergo the temperature related strains freely, it would have acquired a length equal to L plus delta L, where delta L is nothing but it's given by L alpha delta T, alpha being the coefficient of thermal expansion. So this would have been its unconstrained length. In one extreme situation where it's totally unconstrained and the other fully constrained, so the actual situation will be in between the two. So how do we tackle it? The easy way is that we convert the temperature effect into fixed ended forces. So that is, we first apply artificial fixities, and when we apply the artificial fixities and then allow the temperature to rise, then this will give rise to fixed ended forces as we have shown here, and the value of the fixed ended force is nothing but equal to EA by L multiplied by the change in length as compared to the unconstrained length of the member. So that we have already seen that delta L is L alpha delta T, so we get the fixed ended force as EA alpha delta T. Now we apply equal and opposite of these fixed ended forces on the actual structure. So we have our structure here with all the degrees of freedom labeled, and we just apply the opposite of the fixed-ended forces on the relevant joints, that is the two joints at the ends of the member. Now we can form our load vector. So this is our load vector, and we have marked the various degrees of freedom also. So because of the thermal effect, the forces would be along the degrees of freedom number 4 and number 7 only. And these directions are consistent with the analysis we have done, because here the temperature is rising. That means the fixed-ended forces would be like this, that is, they would tend to keep the particular member under compression. So opposite of these would be acting on the joints. So in a sense, we have to analyze two structures. One is the case of the fixed-ended forces, the structure under restraints, that is structure A, and the other is the structure with the opposite of the fixed-ended forces applied. So what we do now, we solve structure B using the matrix approach, the direct stiffness approach, and after solution we obtain the displacements and the member forces. Once we have done that, then the final member and forces can be obtained by superimposing structure B, its results, with those of structure A. So structure A's results are known. It only has the axial force, for example here compressive force of EA alpha delta T, so that has to be superimposed with whatever the forces we get from the analysis of structure B. So after we have completed this process, then we get the final results. Now what will happen, suppose the temperature had fallen down. Here we are assuming delta T to be positive, so temperature has risen, but in case the opposite happens, then the only effect it will have is that the direction of the fixed-ended forces will be opposite to what are shown here, and same logic will apply to the equivalent joint loads. So here in the load vector, this term would be positive and this term would be negative. Now something very similar to thermal effects is the lack of it. Now lack of it happens usually at site. So it is basically a kind of flaw associated with the fabrication, that if the fabrication is not proper, a member may be either shorter or longer than the ideal fabrication length. So this is something similar to temperature effect. So it can be tackled in the same way as we have done for the case of the temperature. So if the member is a longer member, so this is analogous to temperature rise. So here the fixed-ended forces would be such that the member would be in compression, and in the case of shorter member, then this is analogous to temperature fall. So these can be tackled in the same way as the thermal effect. Now after thermal effect, the next complication we introduce is the hinge or guided supports. So far we have assumed that all our supports, they are fixed. Now let us consider this structure where one of the supports is like a roller. So how do we tackle this kind of situation? As we have said before, we have to incorporate this without fundamentally changing our background analysis approach. So let's see how do we do it. So before we go ahead, let's consider a hypothetical case that structure had all the joints fully restrained, including the one with the hinge. Then what would have been the change? Now if this would have been the case, this case we could have tackled similar to what we have learned before. We would just number the degrees of freedom such that the unrestrained joints are numbered first. So we have only 6 degrees of freedom, and remaining numbers are associated with the reactions. So that means we have KTS 15 by 15, out of which KPP will be 6 by 6. So P and X, the partition of the load vector and the reactions, and the partition of the matrix KTS into KPP, KXX, KXP and KPX would be such that the partition would be at row 6. So the size of the load vector would be 6 by 1 and that of the reaction vector would be 9 by 1. So this we are very familiar. Now let's do one more hypothetical situation, that suppose this end were totally free. So we just remove this restraint, then how would we tackle this kind of situation that there is no restraint at all at this particular joint? So think about it. So this you could have done very easily, that in this case you would have numbered these degrees of freedom in continuity with the unrestrained joints. So that is the size of the P and X would vary, but KTS would remain same. So here P would have been 9 by 1, X would have been 6 by 1, KXX 6 by 6 and KPP 9 by 9, but KTS would remain same. And because there are no loads acting along these degrees of freedom, the corresponding entries in the load vector P7, P8 and P9 would all be 0. Now we come back to our actual case which we want to solve. Now, having learned the previous two hypothetical cases, this would be now easy. So what we have done here is that we have already numbered all the degrees of freedom and also all the degrees of freedom associated with reactions, and we have just kept the numbers here so that you can make a guess. So we have only numbers left here, 7, 8, 9. How would we? In ordinary situation we would have numbered 7 like this, and we would have numbered 8 vertically up. However, we find that along the vertical direction this particular joint is restrained. So we do a modified numbering. So we first number the rotation here and number the degree of freedom associated with the vertical reaction in the end, so that we can club it with the reactions. So that's how we have adjusted the numbering at this joint. So this is essential so that we don't mix the load terms with the reaction terms. Otherwise we will not be able to do this kind of partitioning and we will not be able to solve if the two are mixed together. So now what has changed is that as compared to the previous two scenarios, KTS has again not changed. So this renumbering has only changed P and X and the partitioning. So KTS on whole has not undergone any change. So we have the size of P 8 by 1, X 7 by 1, KPP and KXX 8 by 8 and 7 by 7 respectively. So now if we see the situation here, P7 and P8 they are 0 because apparently there is no load acting as of now. However, after inputting all the values, when we solve, in the end we'll get all the displacements. So loads being 0 does not imply that the corresponding displacements are also 0. They would have some values. Now we bring one more complication. Let's say that we have the same structure with the hinge and we have numbered the degrees of freedom like the previous case, but the only difference is that now along this joint there is a moment M not acting. How would this change the situation? So think about it, how this brings about change either in the KTS or load vector or any other aspect. So if we think closely, we can incorporate it very easily. So nothing would change as compared to the previous scenario. Only change would be that earlier we were considering 0 value of the load corresponding to the degree of freedom 8, and now what we are finding is that there is a moment M not acting along the degree of freedom 8, which is the rotation degree of freedom. So here in this particular case the only difference will be that P8 has to be considered equal to M naught, and after we solve the system then we'll get all the displacements including the rotation along this degree of freedom. Now it must be noted that because we know from equilibrium, an external force or moment acting at a joint is equal to the sum of the member end forces or moments of all the members meeting at that particular joint. So here there is only one member, so by this logic the member end moment at the end of this particular member will be m0 and in the same direction. Now we bring one more complication, that let's say we have UDL here. So we have the structure, but deliberately we have posted the UDL in this particular member which is adjacent to the one having the hinge, and in the next scenario we'll bring the UDL here also. But let's first see this case. So in this case, what will there be any change in KTS? We have to convert the UDL into equivalent joint loads. So the answer is that this would change the load vector, but it does not change KTS in any way. Similarly, will there be a change in P and X? Yes, that will be there. So the sizes, they will remain as they were before. So only thing is that we have to incorporate the equivalent joint loads of these, and upon solving we'll get all the displacements. So it's exercise for you that you form the P and the X matrices. So what we'll find that along the degree of freedom 5 and along the degree of freedom 2 there will be equivalent joint loads, and similarly along the degrees of freedom 3 and 6 there will be equivalent joint moments, and these you have to find out by your previous learning. Next, we deliberately bring the UDL on the same span which is housing the hinge. Now how do we tackle this kind of situation? Because now here if we convert into equivalent joint load, then the equivalent joint loads would naturally come along the degrees of freedom associated with the hinge. So how do we incorporate that properly? So this is the restrained member. This particular member has been restrained. So these are the fixed ended forces. So this is structure A. So in structure B we apply equal and opposite of these on the structure which constitutes structure B, and we are showing here the values WL by 2, WL square by 12, and same would be applied on this particular joint also. So here what will change? KTS is same, but here the force vector and reaction vector will change. So if we see closely, because here this WL by 2 is along the degree of freedom 5, so P5 is minus WL by 2, and P6, what will be P6? That will be minus WL square by 12. P8, which is this moment, that will be plus WL square by 12. And now what will happen because of this particular equivalent joint load which is acting along the restraint, along the line of action of the restraint? So we'll have X minus WL by 2. So X9 also gets an additional term. This we have already seen through solved example, that when we write X9 we have to write it as X9 minus WL by 2, so that when we get the final solution, so WL by 2 will go on the right hand side and it will be added. So finally for member end forces we have to do this incorporation, that we have to do correction for the member end forces. Now we'll find that the final member end moment at the right end of this particular member will come out to be 0 once we complete this process. In this particular situation we'll find that the member end moment of this particular member is WL square by 12, and here it is minus WL square by 12. So when we do the addition in the end, the resultant will come out to be 0. Now there is an alternate approach also. Instead of the fixing both the ends, we can take advantage of the presence of the hinge, and we can keep it hinge in the case when we are applying the restraints. So that is, we can consider this structure. However, here the fixed ended forces, they are different. So when we apply the equivalent opposite of this on the actual structure, so the equivalent joint loads will also be different. But now here is the difference. So here in the case of structure A, we are considering the end as hinge, and same is considered when we are analyzing structure B. So the resultant, when we superimpose, that will also be a hinge. So here by these, the final member end moment at this will be 0 automatically. So here in this particular case, our components of the load vector will be like this. So along P5 we will be applying minus 5 WL by 8, that is opposite of the fixed ended forces. Along P6 it will be minus WL square by 8, which is also opposite of the fixed ended forces, and along P8 we would be applying just 0. Now after we complete everything, so in the end we have to do this kind of force correction. But is there any other thing that we need to do here? Because we have now considered a different structure. Yes, we have to do displacement correction also. Why? Because when we do superposition, so for this case A, the deformation of the member is like this. So there is a rotation here, and this rotation has to be corrected in the final solution which we get after solving structure B by the direct stiffness approach. So this was not there in the previous case when both the ends of the member were restrained, because in that particular case there was no displacement in this particular situation. However, now we have a displacement and this has to be added. Now we consider an internal hinge like this. So we are deliberately considering a hinge such that the hinge is in the beam only in this particular joint. So we assume that the column is a continuous member and the beam is connected here in the form of a shear connection, so that hinges in the beam only. So how do we tackle this kind of situation? The previous case the hinge was external at the support, but here we have internal hinge. So we do as usual, we number the members and the degrees of freedom, but there will be change here that we have to do duplication of the degree of freedom. So that is when we do the numbering, 1 for the displacement in the horizontal direction, 2 for the displacement in the vertical direction. But then when it comes to rotation, there will be 2 independent rotations, one for the column members which are continuous, members 1 and 4, and the other for the member 2. So what we have done is we have done duplication of the degree of freedom corresponding to the rotation here. Rest all numbering will be as usual. So we number all the unrestrained degrees of freedom followed by all the restrained degrees of freedom. What we find here is that as compared to the scenario with no hinge, here we have one additional degree of freedom. So here, because of the presence of the internal hinge, the total structure stiffness matrix size will increase. So why this is happening? Because here the hinge is internal. In the previous case hinge was external, so duplication of the degree of freedom was not required, but here because the hinge is internal, so here we need to have a duplication of the degree of freedom, as a result of which the size of the matrix will increase. So we have to just see here that the degree of freedom number 7, for example in this particular joint where we have this degree of freedom 7, so it's common for all the 3 members which are meeting here, 3, 2 and 5. However, here at this particular joint we find that the degree of freedom 3 is related to members 1 and 4 only, and the degree of freedom number 4 is related to member 2 only. So because of this, now when we form our KTS and also the load vector and the reaction vector, the sizes will be like this, because there are 7 degrees of freedom in total. related to the unrestrained joints and the corresponding degrees of freedom. So we have the size of P 7 by 1, X will be 12 by 1, and accordingly the sizes of the various components of KTS will be like this: KPP 7 by 7 and KXX 12 by 12. So it must be noted that earlier we were saying that a particular term of KTS, it has contributions from all the members meeting at that particular joint, but this won't be happening here, because now at this particular joint corresponding to rotation there are 2 degrees of freedom, 3 and 4. So members 1 and 4 will make contribution to the degree of freedom 3, and member 2 will make contribution to degree of freedom 4. So this has to be taken care of in the code number approach. So when we form the association matrices, the association matrices should be properly made. So for example, for member number 2, the association matrix would be like this. So note that we have here the number 4, which is corresponding to the rotation. Here 1 and 2, they are corresponding to the 2 translations, 4 is corresponding to the rotation. Now when we form the association matrix for member number 4, what we find is that at this end there is the numbers are 14, 15, 16, and at the top end we have the numbers 1, 2 and 3. So 3 is corresponding to the rotation associated with the 2 columns. So the 2 are now different. So that's how the terms will go to appropriate locations of KTS. So members 1 and 4, they will make contribution to a common location of the KTS, but member 2 will not make to same location. Now what happens if we have internal hinge but UDL? So all we have to do is, now we consider the case of the equivalent joint loads, and then we can form our load vector. P1 is 0, P2 we have minus WL by 2, P3 is again 0 because we have hinge here, because now the influence of all the UDL is absorbed by the degree of freedom 4 only. So P3 will not receive any contribution, and P4 will be minus WL's curvature. So this has to be understood. Then P5 is again 0 because axial component. P6 will be equal to minus WL by 2, and P7 will be equal to plus WL square by 12. Or alternatively, we can consider a different structure for the case of the fixed ended forces like this. So where we have assumed fixity at the right end, and the left end we have deliberately kept hinge. So remember that here we are showing degree of freedom 4 corresponding to this member, and not the degree of freedom 3. So here the various components of the equivalent joint loads will be different. Just like we have correction for the member and forces, so similarly we have corporate correction for the member and displacements also, because this particular structure will have rotation at this end, and this has to be added to the final rotation we get at the after solving the system of equations. Now how is the previous case different from this case, where the hinge is common to all the beams and columns meeting at the joint? Now here there would be a triplication of the degree of freedom corresponding to rotation. Instead of one common degree of freedom like this, and there will be 3 different rotations here, each corresponding to different members meeting here, and then rest of the numbering will be as before, but only thing is that 2 numbers have increased. So here the total size of KTS has become 20 by 20. So here we can see that corresponding to rotation, all the members meeting at this particular joint, they have independent degrees of freedom. So it's kind of triplication rather than duplication. So we have till now studied how we can incorporate the presence of hinges, both external as well as internal. In the case of external hinge, the size and the constitution of the KTS does not change, but if there is an internal hinge, then it does change. Now we introduce an alternate approach where we don't involve any kind of duplication of the degree of freedom. But here the stiffness matrix itself is modified. Let's see, we have this member where the left end has a hinge. So this approach considers that the hinges are permanent one. So the boundary condition of the member having hinge on the left side will be retained at all stages. So what this technique involves is, it involves modifying the member stiffness matrix itself. So the corresponding rotation shall not be logged while we derive the member stiffness matrix. So this approach is very similar to the modified approach in the case of moment distribution method and also slope deflection method, when the far end is say hinge. So we have different coefficients in the two methods. So this approach is quite similar to that one. So let's derive the modified stiffness matrix for this particular situation, and here we have the same member and this is the modified stiffness matrix in terms of the local coordinate system, and you can derive it yourself. What we'll do, we'll derive the second column. So to do that, we apply a unit displacement along the second degree of freedom and find out what are the forces developed along the various degrees of freedom. So here we have to make sure that we allow the rotation at this particular node, and by making use of the first principles using the basic slope deflection relations, we can find out the forces generated along various degrees of freedom, and they will be the members of the second column of the local stiffness matrix. So we know that the force required here will be 3I by L cube because the member is bending like a cantilever. So this term is basically K22 by definition. What is K32? K32 is basically the moment developed in this direction, which is supposed to be 0 because we are considering hinge here. So K32 is 0. Next, K42 will anyway be 0 because it's related to the axial effect, and we have already made assumption that bending and the axial effects, they are independent of each other. Now we go further and we find out the reaction at the other end of the member, which will be opposite to the force applied here. So that will be 3I by L cube. That's why the corresponding term K52 is minus 3I by L cube. And finally, by making use of the moment equilibrium, we can find out that the moment developed at this particular end is 3I by L square, and this is nothing but it's equal to K62. So that's how we have derived the second column of the stiffness matrix. Now by same logic we can derive the other columns. But in all cases we'll find that when we are deriving different columns, the terms corresponding to the third row, for example here K32, will be 0. So in general we'll find that the third row is 0, and because the matrix is symmetric, that means that the third column is also 0. So this is the important observation we make in this particular case. Next, let's say we have this structure which we have already considered previously, and this has a hinge in the beam. So the column is continuous and we have the hinge which is making a shear connection. So here we again use the code number approach, but we don't involve any kind of duplication as in the previous approach. So here we have marked the degrees of freedom as usual. So this degree of freedom 3 is marked here also, but now we'll use the modified stiffness matrix of member number 2 instead of the original one, whereas for members number 1 and 4 we'll use the normal stiffness matrix. So what we find here, that by this automatically member 2 will not make any contribution in the third row or third column of KTS, because the corresponding row and column of this particular member stiffness matrix, they are 0. However, members 1 and 4, they will make contribution as before. For example, for member number 1, basically the third member degree of freedom, it coincides with the third structure degree of freedom, and similarly for case of member 4, the sixth member degree of freedom corresponding to this rotation coincides with the structure degree of freedom 3. So they will be making contributions. However, for member number 2, because the third row and third column are 0, so no contribution will transfer. Now when we solve the system of equations by the method which we have already learned, and when we find all the displacements in the end, the displacement we get along this degree of freedom will be corresponding to the rotation of the column only. We will not get any chance to know how much rotation has occurred in this member number 2. Now if we have a hinge passing through all the three members, the columns and the beam, then we have to look it more carefully. Now in this particular case, when we do the numbering and we have this kind of situation, and because there are three members which are meeting at this joint and each of them have hinge at one of the ends, so we have to use modified stiffness matrix for all the three members. Now it depends on which end is your near end and which end is your far end. So far we have derived the modified stiffness approach when the near end is hinge. So in the case of member number 4, it's the far end if you are considering the bottom joint as the first or the near joint and the top joint as the far joint, so that our local x-axis is directly upwards. So in that case we need to derive the modified stiffness matrix for member number 4 for that kind of situation, that the far end is hinge, just like we have derived for the case near end is hinge. So in any way, when we do all the computations and when we form the stiffness matrix, we find that all the three members, they will not transfer any term corresponding to the structure degree of freedom number 3. So we'll find that its third row and third column will all be 0, because all the three members, they are having this kind of constitution of the member stiffness matrices, and as such along the diagonal of the KTS will have a 0 term at the third row and third column location. Hence this matrix will be singular, so its determinant will be 0, and we will not be able to find its inverse. When we are solving this system of equations, we will encounter runtime error. So how this error has come? This error has come because of the numerical issues involved here. So this can be very easily solved. All we have to do is that we all together eliminate this particular degree of freedom itself. So what we have to do, we have to just renumber the various degrees of freedom, and this particular degree of freedom we have to all together skip. So that means that we don't consider any number associated with this degree of freedom. So our structure is like this now, with all the degrees of freedom marked. So at the hinge location we are considering only the two translations, and we are not considering any rotation. We have altogether skipped it for the reasons we have outlined, and then we have the number 3 continuing here. So the result will be that KTS will be now 17 by 17 instead of 18 by 18. So we have skipped that particular degree of freedom so that we don't encounter the situation of runtime error. So this way we can do the solution. However, we'll not get the displacement of any of the three members. Other issue is the equivalent joint loads. Now we have considered hinge here. So what will be our structure A? So in that case, the equivalent joint loads must be computed by using the condition that there is a hinge, and then when we are in the end doing the correction for the fixed ended forces, then we don't need to consider any kind of correction for the displacements. So in this particular case, we don't have any choice like in the case of the previous approach, where we had choice either we could fix both the ends or we could keep one as hinge. Here, because we have considered a permanent hinge, so we have to consider it hinged at the time of obtaining the equivalent joint loads also. So displacement correction will not be applicable corresponding to the rotor here. So we have covered in detail how to tackle the presence of the hinge, both internal and external, and in the next class we will cover through some of the solved examples. So we are just showing here some of the structures. You can just try solving these conceptually, and we'll have discussion in detailed manner in the next class. Thank you very much.